practical introduction to polar codes. So in the last two parts, we were discussing about some very fundamentals of polar codes. So what polar codes have inside them, and then we saw the basic construction of polar codes. In this part, in this part and the next part, we are going to see the actual critical parts of polar codes, namely the encoding and decoding. So in the construction part, we have decided some certain parameter which is going to be used in these two blocks. So these are the three blocks, and we are going to see encoding now. So just some notation. Trust me, this is not very difficult. So there are just three parameters: n, k, and I. Nk you must be already very familiar. N is the block length. After adding the redundancy, k is the message length. So, and what is this I, script I? Script I denotes a set. It is directly related to the set that we decided in the construction phase. We have decided some set j in the construction phase. Just take all those indices, apply the bit reversal operation on each index, and form a new set I. This set is called information bit indices, and the complementary set is called frozen bit indices. That's as simple as that. What is this bit reversal operation? Bit reversal operation is simply take the binary representation of a given integer index in n bits, because every index is going to be less than or equal to 2 per small n. Therefore n bits is sufficient to represent every index. Just take every index, represent in binary form, reverse the order of just reverse this order of binary numbers, and then get the new integer and take that integer into the set script I. So that's all. So another binary kernel that we are going to critically use in this encoding process is this kernel, which is often called as Arikan's kernel sometimes, and is also very well known kernel. So this kernel is triangular, and we are going to apply several Kronecker product operations. As a result, the matrix dimensions increase, it gets doubled every iteration. So we start with a 2 by 2 size, and then it grows to 4 by 4 size, and then now it is 8 by 8 size, and so on. So the dimensions grow as a power of small n. So we are going to use this in the encoding process, as you see very soon. So what is encoding? Encoding is as simple as using the kernel to multiply a vector and get the encoded vector. This is very similar to the traditional encoding step, where you multiply the k message bits directly with a generator matrix and get your encoded message vector, where the redundancy added, and you have n bits in this stage. Because we have only k bits in the initial to start with, we have k bits, and we have converted them into small capital N number of bits. But here, if you see, D is not messaged directly, but rather message is embedded inside D. And this is not a generator matrix, it contains generator matrix, as you are going to see very soon. So how D is formed? It is very simple. Take the information bit indices, embed your message inside that, and then rest of the bits just simply freeze them, force zeros at those indices. So this message is going to vary based on what you are going to transmit, but this is always 0. As a result, what you are going to see is something very similar to the matrix multiplication with a rectangular matrix, because this is k bits and this is n bits. This is k bits and this is n bits. We are supposed to multiply with a rectangular matrix essentially. That is also embedded in this equation in an interesting fashion. So just take an example. N is 8, k is 5, and then information bit indices set is this 5 indices. What we are essentially doing is this matrix multiplication, because the kernel, after doing 3 Kronecker products, becomes this big matrix of 8 by 8 size. What we are doing is forcing some of them to zeros. These are frozen bit indices, the complementary information bit indices set. So in the remaining bit indices, we have some data, but these zeros are forced. As a result, these columns are removed in effect. So we are essentially using only some of these columns to transmit our information. So we actually have an equations very similar to the original traditional or classic form of linear encoding. So it's not very different from that in that sense. Only thing is, how do you implement this particular equation? Because it is matrix multiplication. Usually, matrix multiplication is of quadratic complexity, which may not be as implementation friendly as a as a lesser complexity implementations. And since we are talking about polar codes which are asymptotically good, we are supposed to use higher block lengths, and at those block lengths quality complexity is not so friendly. So we are supposed to go to higher more efficient implementations, and luckily we do have one. So in fact it reduces order of n square implementation to a very menial order of n log n implementation. So what is this efficient implementation? This is simply this butterfly circuit where there are several XOR operations being performed on the given D is going to be converted into X. Okay, that should be very straightforward. Once you okay, if it is not so straightforward, I'll show you one small thing. So if you consider this block is going to implement one kernel. So as a result, what you're going to see is f times whatever input that is going to come in, and this is another f, and this is another f, and this is another f, and this XOR, if you take, this is an slightly stretched, but it is also another f, and so on. So by cascading in an intelligent fashion several small f's, we are going to essentially implement the n-fold Kronecker product in an efficiently computable fashion. So there is some notation that you can use. So there are several stages, smaller number of stages will be there in general. So because this is n equals to 2 power 3, there are three stages. And every stretched circuit can be represented with these terms, which I use often. So lower branch, upper branch, and a connection. So that's how it goes. So yeah, this is a pretty efficient implementation. You can write a MATLAB code with a reasonable understanding of this circuit, or you can use our MATLAB code. So we have provided whatever code that we have given. We have provided some very efficient implementation over there. So just download that stuff and use a simple function p-encode. So u is a message of k bits, and simply by calling p-encode function, it is going to use x. So one important thing is the function init_pc, which performs the construction of polar code, should have been already called. As I was explaining in the last part of the tutorial, init_pc should have been already called. Then only this function will work properly, because the indices, the frozen bit indices, has to be known prior to encoding. That is the usual encoding. And there is an interesting thing here. There is an interesting version of encoding any linear block code, which is also very interesting for the practical implementations for several other reasons. So that is called systematic encoding of linear block codes in general. So if we can extend that systematic encoding to polar codes, it will be very interesting. So that is some interesting work that is done in this second reference. So as a result, we have some very efficient, in fact equally efficient encoding as the non-systematic versions, which is already very efficient. So we want, in case you want a systematic version, this should be as efficient as that. So except for scalar factors, we have several range of algorithms in this particular paper. So that is they are also implemented in the MATLAB code that we have provided to you. So as a result, you have this simple function call. This will implement whatever you wanted. So just pass, if you use p-encode function, this will non-systematically encode the standard polar code. This is the systematic variant of the polar encoder, systematic variant of the polar code, which will simply encode it in a systematic fashion. By the way, systematic coding is nothing but when you it 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 represents the entire encoding process as an appending process of redundancy. So in general, after doing the encoding, you may not see the message bits as it is in the encoded bits, though we colloquially say that we redundancy being added or appended. The redundancy is added in a very linear fashion um, within the n bits that are being output. But in case you can retain sustain the message bits as it is in the code word, that is called systematic encoding. That's why they are interesting. Interested readers can read any standard text on coding theory that can help you understand systematic versions, but this is just an add-on. So standard polar encoding is something sufficient from these two lines. And that finishes the encoding part. So we will move on to decoder in the next part of my tutorial. Thank you very much for watching. Keep watching my last part. Thank you.